Every structure so far has been a line. Arrays, linked lists, tags, queues. You walk them front to back. But a lot of real data isn't a line. A folder holds folders, which hold more folders. A company has a boss, then managers, then teams. That branching shape is a tree. And the right kind, a balanced search tree, can narrow a million items down to about 20 steps. Let's build up to that. A tree is a set of nodes joined by edges into a hierarchy. At the top sits one special node, the root. Every other node hangs below it, connected by a single edge to the node above, its parent. The nodes just below a parent are its children, and a node with no children is a leaf. One more idea we lean on constantly. Any node plus everything beneath it forms a subtree. So a tree is built from smaller trees. Every child is the root of its own. That self similarity is exactly why trees and recursion go hand in hand. There are many kinds of trees, but start with the binary tree. Its rule is simple. Every node has at most two children, a left child and a right child, both, one, or none. That tiny limit gives the structure a clean two-way shape. And in the moment, once we add an ordering rule, those two directions, left or right, become the key to searching fast. Two measurements matter. The depth of a node is how far down it sits, the number of edges from the root, so the root has depth 0. The height of the tree is the longest path from the root down to a leaf. Height is the one to watch because almost every tree operation costs time proportional to it. A short, bushy tree is fast, a tall, stringy one is slow. Keeping the height small is the whole game. How is the node built? If you saw the linked list episode, this rhymes. A linked list node held a value and one pointer to the next node. A binary tree node holds a value and two pointers, one to its left child, one to its right. If a child is missing, that pointer is just null. That's the whole building block. Wire them together, root downward, and you have a binary tree. To use a tree, you often need to visit every node. Down a line, you'd just walk end to end. But a tree branches, so there's more than one order. Two families. Depth first dives down a branch before backing up. Breadth first sweeps across level by level. The most useful depth first order is in order, and its rule is the same at every node. Visit the whole left subtree, then the node, then the whole right subtree. Left, node, right. Watch it snake through, always finishing the left before touching a node, and the node before going right. Remember this order, it has a payoff coming. Move when you handle the node and you get two more orders. Pre-order takes the node first, then left, then right, useful for copying a tree or saving its structure. Post order does both, subtrees first and the node last, used to safely delete a tree or evaluate an expression bottom up. Same three pieces, just a different moment for the node. The breadth first order is level order, and it's the odd one out, no recursion. It uses a queue, the structure from our last video. Put the root in the queue, then repeat. Take the node at the front, visit it, and add its children to the back. Because children always join behind the current level, you finish each level before the next begins. Top to bottom, left to right. Now the rule that makes trees shine, a binary search tree, BST, keeps one promise at every node. Its entire left subtree is smaller and its entire right subtree is larger. Not just the immediate children, the whole left side is smaller, the whole right side larger. And here's the payoff from earlier. Run an in-order traversal, left, node, right, on a search tree, and the values come out in perfect sorted order for free. A sorted array gives fast search, but inserting or deleting can be slow because items have to shift over. A balanced search tree keeps everything in order while still allowing fast search, insert, and delete. Searching is where it pays off. Start at the root and compare. Smaller, go left. Larger, go right. Equal, found it. The power is that in a balanced tree, each comparison discards a large part of what's left, often close to half, in a single step. It's binary search living inside a tree. In a balanced tree of a million nodes, you reach any value in about 20 comparisons. That's order log n. Inserting works the same way. Pretend to search for the new value, smaller left, larger right, until you fall off the tree at an empty spot. That spot is exactly where the value belongs to keep the ordering true, so you attach a new leaf right there. No shuffling, no resizing. Walk down and drop it in. And to keep things simple, if the value is already there, we just ignore it. Like search, it costs time proportional to the height. Deleting is the trickiest, with three cases, and here are three separate examples so they don't get tangled. If the node is a leaf, just remove it. If it has a single child, lift that child up into its place. The hard case is two children. You can't just rip it out, so you find its in-order successor, the smallest value in its right subtree. Copy that value up into the node, then delete the successor, which always has at most one child. The order stays intact and the tree keeps working. Deleting is the trickiest, with three cases, and here are three separate examples so they don't get tangled. If the node is a leaf, just remove it. If it has a single child, lift that child up into its place. The hard case is two children. You can't just rip it out, so you find its in-order successor, the smallest value in its right subtree. Copy that value up into the node, then delete the successor, which always has at most one child. The order stays intact and the tree keeps working. The numbers together. In a balanced binary search tree, search, insert, and delete are all order log n, wonderfully fast. In the worst case, an unbalanced tree, they degrade to order n. Any full traversal is order n since you must touch every node, and the tree uses order n space. The headline: a binary search tree is fast only when it's balanced. Keep it balanced and order log n is yours. Where do trees show up? Almost anywhere hierarchy or ordering matters. Your file system is a tree of folders. Databases keep their indexes as trees, so lookups stay fast. Autocomplete often runs on a special kind of tree called a trie. The heap behind a priority queue is a tree. A compiler even passes your code into a tree. All trees. Reach for a binary search tree when you need a set or map that stays sorted while still supporting fast search, insert, and delete. If you only ever look things up and never need order, a hash table is faster. But the moment you need sorted order, the tree wins. In code, the structure mirrors the idea. A node holds a value and two links left and right, each starting null. To search, recurse. Empty means not found, a match means found, otherwise compare and go left or right. To insert the same shape, if the spot is empty, create the node, otherwise compare and recurse down. Notice how the code follows the tree. Every call just steps into one smaller subtree. To wrap up, a tree is a hierarchy of nodes, one root branching into subtrees. A binary tree gives each node at most two children. You visit nodes depth first, in order, pre-order, post-order, or breadth first, level by level with a queue. A binary search tree adds one rule, smaller left, larger right, making search, insert, and delete order log n, and making an in-order walk come out sorted. But only while it stays balanced. Feed it sorted data and it becomes a line. Reach for a tree when you need hierarchy or sorted data with fast updates. If this made trees click, please subscribe and tell me in the comments what to explain next. Self-balancing trees, heaps, graphs. Your vote could become our next video.